Previously, I built and trained a simple XGBoost machine learning model to predict stock prices. This time, I enhanced the model with hyperparameter tuning to predict stock price. Has the model performance improved? Let's find out. For those who are interested in the previous video, I will share the link to my first video on screen and in the description box as well. We will load the dataset using the SPX index stock closing price as the prediction target. I will set the time period to be 6 years from 2020 till the end of 2025, so that we have 5 years of training data from 2020 to 2024, and the last year of 2025 to be our test dataset. The time interval used is 1 week. Moving on, we have the features and trading indicators that I have coded to be used as model training inputs. You can see that they are quite varied, from high and low prices for the time period, to sin month, to ADX strength, and even various candlestick patterns. Some of the trading indicators that I have used here are the raw numbers, and not a binary buy or sell indicator, as XGBoost model can handle the raw inputs better. I will also be excluding some of the raw moving average values from the dataset later. The feature engineering phase is important, and it is up to you to use your creativity, so feel free to explore and use any features or indicators you like. You never know, you may find some surprisingly uncorrelated features that may be a good predictor for stock prices. After feature engineering is done, we will split the dataset into 5 years of training data and the last year of 2025 as test data. We will remove some of the unused features here too. Then, we can fit a baseline XGBoost Regression model with default parameters to the data. We will first inspect two performance metrics, root mean squared error and mean absolute percentage error, to evaluate the model performance based on the test dataset. As you can see, the model is not good at stock price prediction, with a high deviation from the predicted price, and a percentage error of around 7%, which is not good enough for me. Apart from the two performance metrics we just went through, I thought of using other custom design metrics for evaluation as well. I wanted to find out if the model has different prediction bias for up and down days. Thus, I created an additional column to measure the difference in percentage change for day-on-day close price change versus day-on-day predicting close price. We can then use these measures to calculate the mean and standard deviation of the difference in percentage change for up days and down days. The results are interesting. The mean percentage change difference for a down day is -1.2 and the mean for an up day is approximately 1, which suggests that the model predicts a more conservative percentage change for both up and down days. Meaning to say, if the actual day close-up percentage change is 2%, on average the model only predicts a percentage change difference of 1%, making the model prediction more conservative in price change estimations. Looking at the standard deviation of approximately 1.9% in both directions, it suggests high variability across the days. We can plot various charts to inspect the data further visually. First, let's do a KDE plot of the percentage change difference between actual and predicted close, split between up and down days. Visually for both up and down days, they resemble normal distributions with higher kurtosis. This aligns with what we saw previously for the mean of percentage change difference as well. The skewness at the tail end of both distributions also suggests that more often than not, the predicted price change movement is similar to the actual price change movement, be it either up or down. We can also plot a bar plot to visualize it in another way. We can see that there is significant variability across the year. Ideally, we would like to see small or no bars at all, which would mean the predicted prices are close to actual prices. This chart also confirms our previous findings. Lastly, a line plot comparison is yet another way of visualization as well. This would be an easier way of seeing the variance between actual and predicted price change difference. Apart from the previous plots, we can also do a feature importance plot to inspect the top contributing features to the model prediction. As there are a number of features, it can seem cluttered, so we can do a table to view the top 10 features as well. From here, we can see that the closing price is the most dominant feature in model prediction. We can also plot a chart of actual close price versus predicted close price to assess the model prediction. In the beginning, we can see that the model's predicted price is fairly decently, being able to track the actual close price closely. However, if we look at the results from mid-May 2025 onwards, we will notice that after predicting which is close to the actual price, the model predicted price starts to deviate from the actual close price, and it is consistently being underpredicted, and the difference between the actual and predicted price actually increased over time. This is an interesting observation worth noting for now. Apart from training the XGB model with the default parameter settings, we can perform hyperparameter tuning to make slight adjustments to the model to affect changes to how the model is trained. For this, I created 5 different models with different numbers of estimators, with some other preset hyperparameters. For the final model, I will use random search CV to find more optimized hyperparameters. There are other libraries out there such as OptTuner or HyperOpt, but I feel that random search CV is sufficient for now. We can create different permutations of models as well. With the 6 model templates, we can run them on 3 years and 10 years of training data to assess the various model performances as well. So, how did it turn out? Honestly, the results are quite a mixed bag. Looking at the metrics, it is not clear that models with hyperparameter tuning will perform better. Model performance varies across the different time horizons of training data. We can also plot predicted prices of the models trained using 5 years of data to observe the results. The results are fairly similar, and we observe the same phenomena where post-mid-May 2025, the difference in price increased through the rest of the year. Similarly, we can plot the predicted prices of the top 3 models with the best evaluation metric based on MAPE. What we see is similar to previous observations as well, where there is a divergence in price starting somewhere during the mid-year, though interestingly, the divergence starts later now. Up till now, the time interval for the training datasets used is 1 week. But what if we reduce the interval to a daily stock price prediction instead? Would the model do better or worse? Let's find out by training 2 models with default parameters, one on 3 years data, and the second on 5 years data. Both models easily ace the performance metrics leaderboard, which is expected with a shorter time interval. The mean close difference percentage change is nearer to 0, and the standard deviation has reduced as well. From the KDE plot, we can see less skewness, and more centrality around the mean. The line plot of the model predicted close price tracks the actual close price better too. As usual, let's plot the daily chart for actual price versus the model predicted price trained using 3 years of data. Interestingly, we see the same divergence occurring, but it starts even later now. This is indeed an interesting phenomena where regardless of trained model, though the better models would predict and track the actual price closer, there will always be a divergence and widening gap between actual and model predicted price sometime later. As of the making of this video, I do not have an explanation, but I will investigate it further and give an update in a subsequent video or in the comment box. If you have any ideas on why this is happening, feel free to comment and let me know. In conclusion, hyperparameter tuning by itself is insufficient to improve model prediction of stock prices. Depending on the model inputs such as training dataset time period and feature inputs, the efficacy of the model will vary accordingly. Apart from that, across the board, the model predicted price tracks the actual close price fairly closely initially. However, midway through, there's typically a point in time where the model predicted price deviates from the actual price. This warrants further investigation. As usual, I have linked the code in the description box for those who are interested in trying it out, but I have left out the code for the model features and trading indicators. And that's the end of the video. Hope you enjoyed it, and if you have any thoughts, feel free to share them in the comment box down below. If you liked this video and would like to see more content of this nature, please be sure to like and subscribe as well. Thanks for watching, and until next time.